Okay, well, hello and welcome to this virtual session. Today I'm going to talk about two-dimensional quantitative comparison of zircon, uranium, lead, and hafnium data from a recently compiled global database. The goal of this talk is to use this global compilation to test hypotheses explaining this late Neoproterozoic hafnium excursion that shows up in samples seemingly from all over the world, including this example in the bottom right from the central Andes, where you can see this major excursion to negative hafnium values at around 600 million years. And the test here is this a global process, a global Earth process, something related to extreme erosion during snowball Earth, or even a paradigm shift in plate tectonic style? Or rather, if this can be explained by regional tectonics related to the amalgamation of the Gondwana supercontinent. Okay, first a quick primer on hafnium. So hafnium-176 is the radiogenic daughter product of lutetium-176 through beta decay. And all of the other hafnium isotopes are stable. Okay, so the 176 to 177 ratio in zircon is very stable following the timing of crystallization, because zircon contains very little lutetium and high amounts of charge-bound hafnium. Now, what most do is normalize this plot to the average chondritic reservoir and plot these data as epsilon hafnium T, where T is the timing of crystallization of that zircon. Now, because zircon is the primary host of hafnium in continental crust, this is a convenient way to think about this type of data, because we can relate back to plate tectonic context. For example, in the bottom left, juvenile melts are typically associated with regions of thin, young continental crust where there's lots of primary mantle extraction, whereas more evolved melts are associated with old, typically thickened continental crust, or the subduction of some ancient passive margin containing abundant, old radiogenic detrital zircon. Now, global compilations have long been used to make large-scale interpretations of Earth processes. So here's early work by Gastiel in 1960, who compiled crystallization dates from around the world. Here's more recent work from Robertson Spencer showing a variety of one-dimensional uranium-lead age distribution compilations on the bottom and two-dimensional epsilon hafnium compilations on the top. And the latter highlights a common way researchers have attempted to simplify the complex data densities shown in this plot by calculating some running average, often to make some interpretation of a global Earth process. Now, more recently, Keller and others have attempted to normalize the sampling in the database by taking the existing data and resampling it inversely to data density. So resampling the troughs in the upper right diagram more than the peaks. What they obtain is a modified database, which they've used to argue for a global phenomenon to explain that negative isotopic excursion in hafnium in the late Neoproterozoic. So we're going to take a slightly different approach to quantitatively evaluating this global database. And let's start with just a simple example here, where on the top we have some one-dimensional data, and on the bottom we have some corresponding two-dimensional data. We can convert the two-dimensional data into bivariate kernel density estimates, which are simply three-dimensional volumes that we visualize in two-dimensional space. For the one-dimensional quantitative comparison, it's actually quite simple. Now, these one-dimensional distributions are not functions, but rather they are discrete arrays of points that share a common x-axis. So one way to quantitatively compare them is to take the geometric mean of each pair of y-axis values and sum them together, and you'll get a number between 0 and 1, where a 1 is a perfect match and a 0 is a complete mismatch. In the detrital zircon literature, this has been extended into other quantitative metrics such as likeness and cross-correlation, each of which also gives you a value between 0 and 1. Now let's take this idea and extend it into two-dimensional space. So here are the bivariate kernel density estimates that I showed before. Now, similar to the one-dimensional case, these two-dimensional distributions are discrete, not arrays, but now they're matrices of points that share common x and y axes. And in a similar fashion to the one-dimensional case, we can simply take the geometric mean of each pair of z-axis values and sum them together to get a value between 0 and 1. And notice that now the value is much lower, suggesting that in consideration of these two-dimensional data, these are very dissimilar distributions. And this can be extended into 2 dimensions also for likeness and cross-correlation, which give similar results, showing that these two-dimensional distributions are quite dissimilar. Okay, so now let's apply these quantitative methods to the global database. And so what I've done here is I've separated out the global database into 8 separate paleocontinents based on Paleozoic sutures and terrain boundaries. And here are the results of that exercise. We have 8 separate paleocontinents, and I'm showing both the one-dimensional uranium-lead age distributions, which are much larger in terms of sample size, and the two-dimensional distributions of age and epsilon hafnium. Now, for the latter, this type of two-dimensional data visualization is quite useful because now we can start to go into each of these individual paleocontinents and pinpoint different orogenic events, and not just in the one-dimensional case in terms of uranium-lead crystallization age, but also in terms of chemistry with consideration of the epsilon hafnium values. Now, with this type of data treatment, we can also start to address the question of whether or not the late Neoproterozoic isotopic excursion to negative hafnium values is indeed the result of some global Earth process. Because if it were, we would predict that that signal should show up on each of the different paleocontinents. And so if we zoom in on that small time interval there, what we see is that negative isotopic excursion is absent in both Baltica, North America, and much of Asian paleocontinents. Okay, so what I want to do now is quantitatively compare these different distributions both in one dimension and two-dimensional space and see how different the results end up. Okay, so here we have the results, one-dimensional comparisons on top and two-dimensional comparisons on bottom. On the left are the actual raw results of the quantitative comparisons shown as pairwise similarity matrices. And on the right is probably an easier way to visualize these results by converting these values into a Cartesian space and showing these as multidimensional scaling plots, where clusters of samples are more similar and more distant samples are more dissimilar. So what you notice is that in the upper right plot, North America and Baltica, so NAM and BAL, these plot very close to Gondwanan-related paleocontinents, such as Perigondwana and South America. Whereas on the bottom right, you can see with the two-dimensional quantitative comparison, these break out quite nicely into Gondwanan paleocontinents on the left and non-Gondwanan paleocontinents on the right. Okay, so let's have a look at Gondwana. So here's a recent reconstruction of Gondwana that highlights major Neoproterozoic to Cambrian sutures involved in the formation of this supercontinent. Now, if you're not used to looking at reconstructions of this particular supercontinent, here in green are the modern land masses involved in its formation. Now, if we compare where we find highly evolved late Neoproterozoic to Cambrian epsilon hafnium values in the global database, for the detrital zircon record, which we're showing here, these are dominantly involved in Gondwana-related paleocontinents and continental land masses. The major pulse involved with India and peri-Gondwanan terrains. And similarly for the igneous zircon record, these highly evolved hafnium values are only associated with Gondwana-related land masses, with major pulses of data found in West Africa and at the southern tip of India. So to conclude, the late Neoproterozoic epsilon hafnium excursion is related only to orogenic events involved with the amalgamation formation of Gondwana. That major excursion is not the product of alternative global processes such as extreme erosion related to snowball Earth or paradigm changes in plate tectonic style. And finally, two-dimensional data visualization and quantitative comparison, as I've shown here today, is a useful way to interrogate paired uranium, lead, and hafnium data, or really any type of two-dimensional data. So with that, I'd like to thank all of these fine people, and thank you for watching this virtual presentation, and enjoy the conference.